Hi guys, Mrs. Soto here. I feel like the last several lessons have been kind of broken up with the SAT and everything, so I wanted to make a quick video recapping everything that was covered in Chapter 6, Parts 2 through 4. So our scenario is that the SAT is designed to be unimodal and symmetric, and the national average on the SAT is 1083 with a standard deviation of 160. So number 1 says we want to draw and label a normal model for the SAT data showing the 68, 95, 99.7 rule. So we're going to draw our normal model, and we know that this data follows a normal model or could follow a normal model because it says that the data is unimodal and symmetric. From here, we're going to start with labeling our mean or average, which was 1083. And we know that these normal models should have 3 standard deviations above and 3 standard deviations below. I did not do a very good job of drawing this symmetrical. Okay, I'm going to figure out what each of these kind of standard deviations away is. So each standard deviation is moving by 160. So I'm going to take 1083 and add 160. So this part here is 1243 plus another 160 plus another 160. I'm going to move the opposite direction, finding standard deviations below the mean. Okay, from here we want to label that 68, 95, 99.7 rule. I'm going to use different colors for each of these. So we know based on this rule that 68% of my data is within 1 standard deviation. So 1 standard deviation below to 1 standard deviation above should show 68% of my data. 2 standard deviations away is our 95% of our data. And then within 3 standard deviations is almost all of our data. This here is 99.7%. Okay, number 2 says Drew scored a 1200 on the SAT. We want to calculate and interpret his z-score. So calculating his z-score is quite easy. We're just going to use our z-score formula, which tells us to take the individual, you could use x or y here, we're subtracting the average and dividing by standard deviation. So for Drew, he scored a 1200. We'll subtract the mean of 1083 and divide by the standard deviation of 160. I'm going to plug this into my calculator. So 1200 minus 1083 divided by 160 gives me a z-score of 0.73. Again, we do want to round to the nearest hundredth, so 2 after the decimal for our z-scores. Now, when we are asked to interpret a z-score, we have to remember that z-scores always measure in standard deviations. So this 0.73 means that Drew scored 0.73 standard deviations above average. I'm going to say on the SAT. This question does pop up on AP exams quite frequently. In order to earn credit, you need to show your work for calculating that z-score, and for your interpretation, you need to make sure that you're noting that the 0.73 is measured in standard deviations. Those are our units, and you need to make sure you're indicating that it was above average because it was positive. Okay, part 3 is asking me to find what percent of students scored above a 1350. So I'm going to start with converting this 1350 into a z-score. I know that eventually I'm going to use my calculator to calculate the percentage, but in order to do that and in order to draw a picture, I need this SAT score to be a z-score. So we'll start there just like we did with Drew. We're taking the individual, so the 1350, subtracting the average, dividing by standard deviation. So I have a z-score of 1.67 after rounding. Once I have my z-score, I have enough information to draw my normal model. Okay, my normal model should have an average of 0 with a standard deviation of 1. We're looking for a z-score of 1.67, so it's going to be somewhere on this right-hand side. And we're looking for the percent that scored above this value. So starting at 1.67, we're going to shade to the right. Our job is to find what percent lies within that shaded area. I'm going to use my calculator here. Because I'm given a z-score and I'm finding the area or the percentage, when I go to second vars, I am going down to normal CDF. My lower bound is where the shaded area starts on the left. My shaded area is 1.67 is where it starts. Ending on the right-hand side for my upper bound, this technically goes on and on forever, so it's ending at just some very large number. And our mean and standard deviation stay the same. So we get 0.0475. So roughly 5% of students score above 1350 on the SAT. Number 4, Allie is told that she is at the 95th percentile for the SAT. We want to find the lowest possible score she could have earned. So number 4 is actually a reversal of number 3. In this case, they're telling me that Allie was at the 95th percentile, which means that she scored better than 95% of students. So when I go to draw my picture here, I have my normal model. I know she scored at the 95th percentile, which means that this shaded area here on the left-hand side is representing 95% of our data. Our job is to find what SAT score is located right there. So the first thing that we'll do is use our calculator to find which z-score represents this lower 95% of the data. So I'm going to second vars, and this time it gives me the percentage, so I'm going down to number 3 where it says inverse norm. The area I'm typing in is to the left at 0.95, and I have 1.64 as my z-score. Now it's asking for what score she could have gotten on the SAT, so my final step is to convert this z-score into an SAT score using my z-score formula. So I know my z-score is the 1.64. The SAT score I don't know, so I'm leaving that variable. I'm going to call it y this time. I'm still subtracting the average of 1083 and dividing by 160 for that standard deviation. We're going to do a little bit of algebra here to get that y by itself. First thing that I would need to do is multiply each side by 160 to get the 160 out of the denominator. And then I would add over the 1083. So this right here is Allie's potential SAT score. If she scored in the 95th percentile, we know at minimum she earned a 1345.4 on the SAT. The last question here asks us to find the IQR for SAT data. I like this question because it does make us think a little bit about what our data looks like and what the IQR is. So we know that IQR represents the middle 50% of our data. So I'm going to draw my picture. I'm looking for the middle 50%. So this area here in the middle is 50%. We are looking for our Q3 and our Q1. Once I have SAT scores for Q3 and Q1, I can subtract them to find that IQR. So I'm going to start with finding what z-score corresponds to this Q1 value. To do that, I need to think about my normal model here. I know that there's 50% falling in this middle area, which means that there should be 50% left in total for the tails. If I divide that by 2, I should get 25% on each of these tails here. So to find the z-score for Q1, I'm going to go back to my second bar's inverse norm. The area I'm using is 0.25. That's on the left-hand tail. And I got a z-score of negative 0.67. Now when I go to find the z-score for Q3, I can go back and do this again, inverse norm. This time I should be at 75%. You might be able to skip this part because it should be the same z-score as we got before, but just positive. Again, that will always happen because these normal models are always symmetric. Now that I have my z-scores, I'm going to convert both of these z-scores into SAT, just like we did up here for Allie. So I have negative 0.67. And I'm also going to set up another little equation using the positive 0.67. Okay, doing a little bit of algebra here. So negative 0.67 times 160 plus 1083. Oops, sorry, you cannot see. Gives me 975.8. This is representing my Q1. Jumping over to the positive 0.67. Again, I'm multiplying by the 160 and then adding 1083. Gives me 1190.2. This represents Q3. The last and final step here is I need to take my Q3 and subtract Q1 to find the actual IQR. So I'm taking that 1190.2, subtracting 975.8 to give me a final answer of 214.4. So definitely a little bit of a trickier problem there for number 5. I like it though because it does kind of combine everything we've learned about normal models along with a little bit from our first part of outcome 1 where we talked about that IQR.